Everyone, and welcome back to our final lesson of topic 3. Today we are going to talk about reflectional and rotational symmetry. Reflectional symmetry is when we look at where are the number of lines of reflection that will map our figure onto itself. So for instance, in this figure that they are giving us in the first example, we have two different lines of reflectional symmetry. Line M allows us to fold our figure over it and so that it would map onto itself. Line N does the same thing. It cuts it horizontally and we can map it onto itself. We could potentially try and see, okay, are there other lines of reflectional symmetry? For instance, because I cut it through this way. The problem is if we mapped it on top of itself, this would fold down here and it wouldn't be directly on top of itself. So we only have the two lines of reflectional symmetry. We have a few more examples then down below. We have a vertical line through this isosceles triangle that can be drawn in so that this is folded on top of itself. So there is reflectional symmetry. The problem with an isosceles triangle, though, is if we then tried to draw in, for instance, here, this would not map directly on top of itself over that line. So there really only ends up being one line of reflectional symmetry. In our second figure, a rectangle, we could draw in two lines of reflectional symmetry. So again, yes, it does exist. Now, again, some people like to think, oh, are they through the diagonals as well? But if we try to map, again, reflecting over that line, it wouldn't fold directly on top of itself. It would be off the picture. So we wouldn't be able to say that this has reflectional symmetry over those diagonal lines, just the vertical and the horizontal. In our last example, in the star-like figure, we could draw in 1, 2, 3, and then we can actually draw in 4, 5, and 6 lines of reflectional symmetry. So again, it does exist, and there are 6 of those lines. Now down below, we have 4 more examples for you to look at using the answer options. Each of these will be used once. How many lines of symmetry does the rhombus have? Isosceles triangle, square, and circle. Now, part 2 of today is the idea of rotational symmetry. And with rotational symmetry, it's the number of times, or the angle at which you would turn a figure in which it would map onto itself. So for instance, if we look at this figure right here, point P, again, if we think about rotating this, okay, we could take this and we could rotate it 180 degrees, and that figure would look exactly like it did in the original. So we would say it has rotational symmetry of 180 degrees. Then it would take going all the way back to the beginning, 360, for it to look like itself. So that's why we would say the original rotation that made it look like itself came at 180 degrees. Now, again, there's 360 degrees total in a full rotation. So you're kind of thinking about the number of turns that you have. Like if you divide 360 by the number of turns, in this case, it was kind of been able to turn 2 different ways to look like itself. That's where we come up with 180. Now, when you have a regular polygon, okay, and again, what is a regular polygon? Those are polygons with the exact same size, angles, and sides throughout. So the angles and the sides are all the same size. We call those a regular polygon. So for instance, an equilateral triangle is considered a regular polygon because all 3 sides would be the same size, all 3 angles end up being the same size. Or square is another example of an equilateral triangle. All 4 sides are the same size, all 4 angles are 90 degrees. Otherwise, other than this, they would tell you it's a regular polygon. And the nice thing about those is we could just take 360 divided by the number of sides, and that would be your angle of rotational symmetry. Now down below we see a square, and again, if we check this out, when we have a square, we could take this square, and it shows you kind of the stages in which it's being rotated. But if we rotate this, we take it and we go 90 degrees, it looks the exact same. 1 turn, 2 turns, it looks the exact same as the original. 3 turns, and then back to the beginning. So what we see with that is there are 4 different turns we can make. So 360 divided by 4 gives us a rotational value of 90 degrees. Every 90 degrees we turn it, it looks the exact same. Down here with our different polygons, for instance, we start off, we have a regular pentagon. So 5-sided figure here. And again, if we take this and we turn this figure 1 time, we see that it looks the exact same as the original. Then we have 2, then we have 3, 4, and then back to the beginning 5, right? Those 5 turns. So we see there is rotational symmetry, and 360 divided by 5 would be 72 degrees for that angle. Again, it's a regular polygon, so you can kind of jump to that. Oh, 360 divided by 5. All right, we get that 72-degree angle. Now the upside down, or the up and down arrow, okay, we take this picture and if we rotate our paper, we could say, okay, if I turn it 90 degrees, it doesn't look the exact same, but when I turn it 180, it did look the exact same, and then back to 360, we see it. So kind of 2 turns made it look like at 2 points in 360 degrees did it look the exact same. So we would say yes, and then again the 360 divided by 2, every 180 degrees we turned it, it looked like the original picture. Last but not least, our isosceles triangle. Okay, if we look at this, we want to again check out, okay, is there something, a rotation that would make it look like itself? Well, on this one, if I take this and I rotate it to this side or on this side, until I get back to the beginning, it does not look like itself. So this one does not have rotational symmetry. So we would say no on this one because the only amount of degrees that made it look like itself was 1 full rotation of 360 would be that angle. So now we have 3 examples below. We have an equilateral triangle for you to try. What would your angle of rotational symmetry be? A rhombus and a regular hexagon. Thanks everyone for watching, and congrats on finishing topic